The next topic is a longer one. We've already seen how once you know the loop gain, you can find the F, you can find the D, you can find the G, the final answer for closed loop gain. Now we've got to go back to the first step, which is how you find the T, which is the basic parameter for the whole feedback system. So the T is found in general, going back to the block diagram again. Here's the single loop feedback system where the boxes have been expanded so I can get a little more inside them, and also a little more specific to do with the connections of the system at the output. So the output of the forward path is represented by the Thevenin equivalent of a generator and a series impedance Z2 feeding into an external load. Connected across the output also is the feedback path, and it usually has a non-infinite input impedance, which are represented by the Z1 in this box, or there's some other impedance there across which the feedback is developed. Now, the first question now of how to calculate the loop gain of the system, the conventional approach is you break the loop. And now, if the Z1 represents input impedance to the feedback path, that has now become unhooked from the output. And what you do to find the T is you apply an independent test signal across the point where you've broken the loop, call that Vx. You follow it around the feedback path through the forward path, which activates the output generator, and you calculate the voltage Vy that shows up on the other side. Now, in the original configuration, the loop gain is the product of the gains of these two stages, which in the block diagram you can identify pretty easily. T is A times K. K, starting from this point, you go through the K box, then you activate this generator with A0, and then you find the voltage back at this point again by using this impedance divider, which is Z1 parallel ZL over the same thing plus Z2. That's the correct answer for the loop gain. But when you calculate it by breaking the loop in that way, you get a different answer, which is pretty obvious, because when you broke the loop, the Z1 got unhooked from the ZL, and that changed the divider ratio. So it changed the final factor in the gain of the forward path. And that's a little more detailed way of saying that when you break the feedback loop, you upset the loading and you get the wrong answer for the loop gain. However, we now have an alternative, because by reformulation of the expression for the closed loop gain, we've buried the A. So we don't need to know what A is separately. All we need to know is the total product T. So how can we calculate that and avoid this problem? Well, the reason we can do better with the T now is that even though we may still break the loop, we are not restricted any longer to breaking the loop at the output or the input of the feedback path, since we don't need to know A separately. We can break the loop anywhere, and we may be able to find a place where we can break the loop without upsetting the loading. So that's the philosophy we're going to use now. We're still going to break the loop, but we're going to look for a place to do it where the loading is not upset. When you start looking at other places, you usually find that such a suitable point is somewhere in the forward path, somewhere inside the forward path. Because when you draw the model of the various amplifier stages, you have some ideal generators in the model. Controlled voltage generators, controlled current generators. So if you break the load at that point, the ideal generators still deliver the same signal, and you don't upset the loading. It's very rare that you can find one of those points inside the feedback path, because the feedback path is passive elements, and the loading is usually significant there. So when you can broaden the problem, you can look at a place now where you can choose a better point where you don't upset the loading. So I'll redraw the picture. And now suppose such a point is part way along the forward path where I can divide the gain into two boxes A1 and A2, such that if I break the loop, I can take the box away now that I've identified the position. Note incidentally, that now that I don't need to know anything about the input or the output or the separation of the boxes, I don't even need to draw the boxes, because the only quantity of interest is the loop gain T, which is represented by this arrow connecting the output back to the input regardless of the interconnections of the feedback path. This is all we need to identify the loop whose gain we're trying to calculate. So now, assuming that this is a point where I can break the loop such that the values of A1 and A2 don't change, that's the constraint, that's the requirement. I'm assuming now this is a point where that's true. Now, having done that, I've avoided the difficulty of upsetting the loading, and I can now calculate the loop gain by applying a test signal at this point, and all I have to do is follow it around the loop back to this point and call it Vy, and Vy over Vx is the loop gain. Obvious by definition. It's the return ratio of the signal to this side of the break to the signal that started out on the other side of the break. So subject to the assumption that A1 and A2 have not changed when I break that connection, this is the correct answer for the loop gain. One little point about this before we go on. Notice the choice of polarities. If I define Vx as positive, it will show up in the other direction of the other side of the break if the feedback is negative. And that's the case that we want to consider. Or qualitatively, in other words, if the voltage Vx goes up a little bit, the voltage Vy goes down a whole lot if the loop gain is large and negative. That polarity relationship is necessary to ensure negative feedback. So what I've done in the picture is define Vy as minus so that Vy over Vx, which is T, is a positive quantity. And that's consistent with its use in the equations that we've had so far, where the denominator is 1 plus T, and T has to be positive. So this is the reason for defining the Vx and the Vy with those polarities. Now, that's the first main point to make about calculating loop gain. The main thing is we've shifted the selection of the point to break the loop in order to find a place where we avoid upsetting the loading. And that's possible because it's only the T we need, and we don't need to know the A separately. Now I'm going to make another modification, which in some ways is even more important than that. Looking ahead to where we actually want to make this measurement. Again, I mentioned this in the introduction, but it's worth going over again. The T is the fundamental important quantity. So we certainly going to want to make a measurement of it directly on the breadboard when we get to that stage in the design. And you can implement this technique directly on the breadboard. You can break the loop, and you can apply an AC test signal and measure what comes out the other end. But there's one step you have to do in between. When you break the loop, the first thing you have to do is apply a DC bias, because you have to reestablish the same DC operating points. And that may be very difficult to do if the loop has a high DC gain, which it would do if it's a DC amplifier, DC coupled, and especially if it's a power supply. They all have huge DC gains. So when you break the loop, the first thing you have to do is reestablish operating point, and it takes a very fine resolution, regulated power supply to do that. And even so, you spend half the time twiddling that knob and adjusting it so the other end of the loop, which is wandering around because of temperature sensitivity and gain variations, it's hard enough even to keep it in the active range, never mind at the right operating point. If you do it this way, you usually end up spending 90% of the measurement time re-establishing operating point and only 10% making the AC measurements. And you don't get very good answers anyway because of the drift in between. So even though in principle on paper this is very simple, in practice it's quite difficult to implement. So what I want to show you now is a very simple modification that totally bypasses that problem. You can set it up in the following way. Here's the same thing again. There's our independent source, assuming that in practice we have re-established operating point. Okay, here's my signal generator, and just to make the things concrete, let's assume that it's 1 millivolt AC, at 1 kilohertz or whatever. I can take a voltmeter and I can hang it across the same point and I measure that 1 millivolt. I take the voltmeter and move it over and measure Vy, and suppose it reads 10 millivolts. Then the loop gain is 10 at that frequency. That's the result we want to measure. But I can also take that voltmeter and I can hang it across this gap. Call that a VZ. What does it read? You've got two choices. It reads 9 or 11. Which one? It's going to read 11 because of the polarities. See, this is plus 1, this is minus 10. VZ is 11. So if I put the voltmeter across there, again assuming it's ideal floating and so on, it's going to read 11 millivolts. Okay, now remember the answer that we looked for is Vy over Vx, which is 10. Now, I'm going to do something different. I'm going to take my signal generator away and put the voltmeter across it and crank up the knob on the signal generator until it reads 11 millivolts. And then I'm going to take the signal generator, which is ideally floating and all that, and I'm going to connect it across the gap, still set to 11 millivolts. And I take the voltmeter and I hang it across Vx. What does it read? 1. And I take the voltmeter and hang it across Vy. What does it read? 10. What's the loop gain? 10. Same as before. So you get the same answer. So what's the difference between the two methods? The difference is the loop is not broken this time. This is an ideal voltage source, zero impedance. The loop remains closed. The circuit topology is exactly the same. The DC connection exists. The loop is self-stabilized. The operating points stay exactly the same, automatically. And you still measure the required ratio. So to put that in words, the first method involved breaking the loop and applying a test signal and measuring Vy over Vx. The second method implies that you don't break the loop, but you inject a test signal into the closed loop. remains closed. And again, you measure Vy over Vx, and you get the same answer, which is what you're looking for, but you've totally bypassed the problem of breaking the loop. Now, I used those numbers, 1, 10, and 11, just to make a concrete example, but of course, the absolute value doesn't matter. It's only the ratios that matter. And when you look at it a little more carefully, you see that the three voltages constitute a phasor triangle. Vz equals Vx plus Vy, which is one constraint over Vx and Vy. Because now the independent test signal is Vz, and you can set that generator whatever level you like, as long as you stay within dynamic range. But both Vx and Vy are dependent quantities now that have to satisfy simultaneously two conditions. One is that the sum of the two of them equals what you apply. The other condition is that the ratio of them equals T, which is fixed by the properties of the system. So it makes no difference to the ratio of Vy over Vx which of the signals is the independent input one. It doesn't matter whether it's Vx or Vz. It doesn't change the ratio of Vy to Vx. In other words, what you measure now is the ratio between two dependent quantities, both of which are functions of the independent input. So, in words, there's tremendous advantage, especially for experimental application, in the use of an injected test signal into the closed loop, because you don't have to break the loop with the consequent bias difficulties. The loop remains in the same configuration. Here's the summary of the phasor triangle conditions. Here's the two equations. Vx plus Vy equals Vz. Vy over Vx equals T. So when you solve those two equations simultaneously, you can find what values Vx and Vy adopt automatically when you impose an arbitrary value of Vz. And this is what you get. Vx is 1 over 1 plus T times Vz. Vy is T over 1 plus T times Vz. That obviously satisfies the two constraints. If you add the two together, you get Vz. If you take the ratio, you get T. And the ratio is what you measure, because T is what you want to find out. It may help also actually to draw the phasor triangle for a few cases, just to see what its configuration is. Suppose you draw the phasor triangle at a low frequency when the loop gain is large. Vz is the independent quantity, so I put that in the reference direction, and it has a fixed length. And the rest of the triangle is formed by a small Vx and a large Vy with a small angle between them, because that's what you get at low frequencies. As the frequency rises, suppose you go to the crossover frequency. At the crossover frequency, Vx and Vy have equal magnitudes. That's the definition of crossover. And the phase angle has increased. So the phasor triangle is now isosceles. If you go to an even higher frequency beyond crossover, Vz is still the same, but now Vx is bigger than Vy, because T is less than 1, and the phase angle gets even bigger. So the phasor triangle gets to be long and skinny again. So you can see, you can visualize an evolution of the triangle as you increase frequency. And you can see that followed through on the oscilloscope if you increase frequency at constant amplitude Vz and you observe Vx and Vy on a scope. you can see the magnitudes and the relative phases going through this evolution. Okay, that's a very powerful technique because of its benefits. So I've said that again right here. It may not be immediately obvious at the moment, but in order to do the injection technique, you still have to choose a point where you don't upset the loading. And we'll come back to that later on. Okay, that's how you go about calculating the t. Now we also want to calculate the g infinity. We can generalize that along with the same model. So here's the basic block diagram again. And notice I'm following the same principle now that we did with the LC filter already. Once you've calculated something to do with the LC filter and you've identified useful quantities for the answer, namely corner frequency, characteristic resistance, and Q factor, when we want to calculate something else to do with the filter, it saves a lot of work if you rewrite the element values directly in terms of the quantities you want in the answer. Let's do the same thing here. We don't want A anymore, we don't want K. So let's invert the definitions and write the forward amplifier gain as T times G infinity and the feedback path as 1 over G infinity, simply substituting the right quantities right from the start. Okay. The loop gain is going to be determined by injection of a test signal into the forward path. I've generalized the signal now to a UZ, and it's represented in the ideal block diagram simply by a summing junction. It's a phasor summing junction, of course, but that's all it's doing. You're just injecting a signal that adds to the signal coming down the forward path, and you identify them with the same notation, same polarity also. Okay. The normal operating condition, just to take the reference, is when the amplifier is operating closed loop, you're not injecting any UZ. UZ is 0 and the UI is not. And in that normal operating condition, if UZ is 0, UX equals minus UY, because the signal just goes straight through. And we know under that condition that the closed loop gain of the system can be written G infinity times T over 1 plus T. That's the final answer we're looking for. To help visualize signal distributions, there's an overlay that suggests the signal magnitude in different places, similar to the one we had for the illustrating the extra element theorem. The width of the trace is a qualitative representation of the signal magnitude. So here you have a small error signal which is amplified in A1, goes straight through, gets amplified again in A2, provides the output and the fed-back signal, which is attenuated and subtracted from the input to give you the small error. So that summarizes normal closed-loop operation with the signal in single input signal UI. Now, we've already seen how you can use the same configuration to find the loop gain. To find the loop gain, you make the input signal 0 and you inject the test signal UZ. And the signal distribution now looks like this. The UZ splits into two. The small part of it is UX if the loop gain is large. UX is multiplied by A2, gets attenuated in the K box, subtracted from 0 because the input is 0, gets amplified again in A1 and shows up as UY. So in this case, it's the wrong picture. In this case, the UI is 0. and you follow the signal from ux back to uy, and you go through the full loop gain to do that. So that's how you calculate loop gain. Uy over ux when ui is 0 is t. That much we've done already also. You can extend that same process to find the g infinity. To find the g infinity, well, let's think a moment about what setup you could use to find g infinity. G infinity is the ideal closed loop gain if the error signal is 0. How can you establish a set of signal conditions in order that you can make the error signal 0? Null double injection. Apply the input signal ui and inject the test signal uz. Two sources. You can choose any other signal in the system you like and null it. That's always possible. So adjust them until you null the error signal. What happens? If the error signal is nulled, the output divided by the input is g infinity, because that's the definition of g infinity. The ratio of output to input when the error signal is vanishingly small. So this is the signal distribution that you set up. Two sources, and you adjust them to null the uy. Because if you null uy, it propagates back to null error signal as well. And under that condition, you then calculate uo over ui, and here are the quantities that go with it. We've nulled uy, so we've nulled the error signal. That means that the fed back signal exactly cancels the input. So uo over g infinity equals ui exactly, or uo over ui equals g infinity. Now you see how this last calculation formalizes what you normally do, as we went through at the beginning of discussing the feedback calculation. The difference is that the way you normally do it, you simply assume the error signal is 0. This way, you actually make it 0, and you calculate exactly the g infinity. Notice that this is equivalent to a simulation of infinite t, because you have a finite output from the forward path, for 0 input, which is like an infinite a, therefore an infinite t. And the way you set it up is you fudged it by using the second input to drive the output to the proper level that takes over the position of the amplified error signal. So you don't need the error signal anymore. That's actually what you're doing when you set up the null condition. You're adjusting the second input in such a way that it drives the output to take over the role of the amplified error signal. So this is another application for null double injection, besides the extra element theorem. Okay, to stop and summarize again for a moment. The feedback path does several things. It provides the feedback signal, which is what it's supposed to do. But it usually does a couple of other things as well. It loads the output, loads the input, and then in a sense that's a non-ideal property. Conventional form of the theorem, you identify A and K, you break the loop and try to find A, but you run into trouble. So instead, redefine different parameters, g infinity and d, ignore the a, and we've just shown in the block diagram generalization how you can calculate g infinity and t and also f and d. Moreover, you can find that all of those quantities without breaking the loop, but instead by injection of a test signal into the closed loop. And the bottom line is you never need to know what the A is. It's always buried inside the T. Now, let's look at how you inject the test signal, because there's other possibilities besides the one we looked at already, which is injecting a series voltage. Here's the block diagram again. The objective is to embody this ideal summing junction. Two conditions have to be satisfied for the injected test signal. It's got to be inside the loop. That's obvious. But it also has to be at a point where you don't upset the loading between the two boxes. That is, you don't change the values of the gains of those boxes. One condition is if you can find somewhere inside the forward loop an ideal voltage generator dependent on some earlier signal feeding into some internal load Z1, this is a point where you could do series voltage injection. This satisfies the two conditions. It's inside the loop, and by injecting the test signal, you don't change the value of this generator. That is, you don't change the output of the box in front of that. And the reason that happens is that when you inject a test signal, you're going to change the current around that loop. But since there's no impedance on the left-hand side, you don't change the value of that voltage generator. That's a little more detailed description of the necessary condition for not upsetting the loading. Because it's a zero impedance voltage generator anyway, so even though the test signal changes the current, it doesn't change the value of the generator. But suppose you can't find an ideal voltage generator somewhere in the forward path, or anywhere. Maybe you can find the opposite extreme. Remember, duality always helps out and doubles the possibilities. So suppose instead you can find an ideal current generator. Then you can do injection by the dual method. You can inject a shunt current, IZ, and it splits into two currents, IX that goes forward, it comes back up again as IY, and the loop gain is IY over IX. And there is a phasor triangle of currents, just the same as there is for voltages, and the loop gain is the ratio of two currents. This satisfies both conditions. It's inside the loop, and it doesn't upset the loading, because even though you change the voltage across the Z1 when you inject the current, changing the voltage across an ideal current generator doesn't change its value. So that's the definition of the condition for not upsetting the loading. So you can measure loop gain by voltage injection or by current injection, but you have to choose the right one. At any arbitrary point, you can't just choose whichever one you feel like. Only one of them can give you the right answer at a particular point, and maybe neither one of them, if you can't find either of these generators. But certainly they're mutually exclusive. You can't have both of them give you the right answer, because they require opposite extremes of condition to be valid. Well, so much for the generalities and block diagrams. Now it's time to get down to a specific circuit example. Okay, let's do a circuit example. A very primitive little audio amplifier. Single-ended Class A power output stage, transformer coupled to a 15 ohm load. there's a driver stage and an interstage network at the beginning, and feedback is taken from the output back to the input. The driver stage is going to be represented simply by a specification that says it has a gain of A1, which is a low frequency value A10 of 8 dB, and it has a single pole at 2 kilohertz. Those numbers imply that the driver itself is a local feedback amplifier in order to achieve those particular results. But that doesn't matter. To go on from here, we just represent the driver by those properties. Now, again, to revert to the conventional analysis, just to illustrate why you run into difficulties, the conventional approach would be to break the feedback path, calculate the forward gain, and then put it back into the closed loop. And the trouble with that is you get the wrong answer, because you've changed the value of A by taking away the feedback path. Because in the normal configuration, the gain of the output stage is partially affected by a current divider, because not all of the transformer current goes into RL, some of it goes down RF. And that needs to be taken into account in calculating the gain of the output stage. And if you take away the feedback path, that factor is different. So you've changed the A. The next step of the usual approach is you recognize that you've done that, and so you try to fudge the loading. You try to put another path across here that represents the input impedance to the feedback path. And this is where you start running into trouble. Because obviously you would draw an RF from this point. The trouble is, what do you do with the other end? Because it doesn't go to ground. So it doesn't go to a zero voltage, so it's no good putting RF just in parallel. You've got to do something else with the other end. Well, what? You don't know. Do you put RF to ground through RS? Or do you put RF to ground through RS parallel the capacitor in R1? And even so, what about the VS? Because that's going to change the current down the path anyway. So you get into trouble when you start trying to fix up the diagram that you've already screwed up. And the same problem applies at the front end. In fact, this case even worse. Because when you disconnect the feedback path, you've changed the loading of the input as well, and you've changed the gain from VS to the driver, which is part of the forward path. And if you try to fix that one up, you draw RF from this point, but you have the same problem. What do you do with the other end of it? Because it doesn't go to ground, really. So that's going to affect the current division in the forward path, and therefore its gain, and you don't know what to do about that either. So again, backing off the conventional approach, let's change the approach to where we have other places to look now for breaking the loop or injecting a signal into the loop. So the first thing to do is to draw an equivalent circuit model. So here's a suitable model representing the whole system. Whether I can get it all in at once. Yeah, just about. First, the power stage. Starting from the voltage V1 on the base of the power stage, it's going to show up across some equivalent input resistance to the power stage, which is going to be 60 ohms in parallel with 30 ohms in parallel with the reflected RE. That is 60 parallel 30 parallel 51 times 3, assuming a beta of 50 for the power transistor. That comes to 17.7 ohms. Actually, the internal RE of the transistor should be accounted for as well, but since it's operating at a 1 amp of DC current, its value is only 25 milliohms, which is negligible compared to 3 ohms. So forget that. So now we've got the representation of the input resistance to the power stage. So V1 is going to develop a voltage across RE of V1 over RE, which will be the emitter current. Multiply that by alpha, which is 1. Multiply the collector current by the transformer ratio, which is N. And so that factor determines the secondary output, and the transformer is included in the current generator coefficient. So the input resistance and the output current is all you need to represent the gain properties of the power output stage. Likewise, all you need to represent the driver stage is infinite input impedance with the voltage VI, represent the output by a Thevenin generator described by the specification, which is a flat gain of 8 dB, a pole at 2 kilohertz, and an output impedance of 4.5 ohms, which is the RB. So that takes care of the forward path, and the rest of it remains explicit as it is in the original picture. Notice again, I've attempted to adopt the basic principle. Before you start doing any analysis and writing equations, make sure you strip down the model so you don't keep anything in it that isn't going to be relevant in the answer. Okay, now we have a linearized model. The loop is closed. Now we want to choose a suitable injection point. Already we take into account the fact we're not going to break it. We're going to use the equivalent technique of injecting the test signal. So where can we inject the test signal? And there are several possibilities. Point P satisfies the conditions for voltage injection because it's right after an ideal voltage generator. So we won't upset the loading if we inject the test signal at point P. So that's a possibility. Point Q is also a possibility. The opposite type. That would be okay for doing shunt current injection because it's right at the output of an ideal current generator with infinite impedance, so that's appropriate for shunt current injection. Either one of those would be all right. Can you see anywhere else you might do injection? Another place to do injection would be right here at VI, voltage injection, because we made the assumption of infinite input impedance to the driver stage. So you could inject a series voltage at this point. And then it would be looking into the infinite impedance. So even though the source impedance isn't zero, the fact that you're looking into an infinite impedance means that you don't upset the loading anyway, because you don't upset the current around that loop, since there isn't any current, because the impedance looking into the op-amp is infinite. Now, in principle, that would be as good a place as P, but in practice it wouldn't be very convenient to do that, or less convenient, because the dynamic range available is less at that point. It's where the signal amplitude is smallest. So you'd have the most difficulty with overloading something and measuring things down in the noise level. So let's not consider that any further. Okay, let's plump for current injection at point Q, at least on paper, if only for the fact that if we do that, we can simplify the model even further. Because if we don't need point P anymore, we can get rid of this whole internal loop. Because all we need to know is what is V1 as a function of VI. We don't need the intermediate loop. So let's just write directly. Basically what we do is we simply solve that internal loop once and for all and get rid of it. Which means that V1 is equal to this coefficient times VI times this resistive divider ratio, RA over RA plus RB. So if you simply make that substitution, you can label this generator as a function of VI instead of a function of V1, and the function is this, where I've simply redefined A10 prime as being the original A10 times the resistive ratio. So having done that, the middle loop can be omitted. And now we simply have this coefficient driving that generator. Again, sometimes it's hard to remember. Before you get too deep, see what you can throw away. Okay, now we're down to this. Same thing. So we've decided we're going to choose point Q to do current injection for the purpose of measuring loop gain and for the purpose of measuring G infinity by using null double injection, which are the two basic parameters we need to solve the problem. So let's do loop gain first. T is IY over IX single injection when the VS is 0. So all you do is follow IX around the loop back to IY. Once again, there's all sorts of different ways you can do that. You can modify the model. You can do some of the algebra on the diagram by loop and node removal by Thevenin's and Norton's theorem. You could do all that. Or you could leave the diagram alone and you could do it by successive voltage dividers. Or you could leave the loop alone and you could do it by successive current dividers. Lots of possibilities. So I'll choose to do it the third way. I'll leave the loop alone. I'm choosing to do that because I'm going to do several calculations on this. So it's a little more convenient to keep the same loop configuration for all of the calculations. So starting with IX, I'll use the current divider approach. The first thing I want to know is how much of the current goes down RF. So the IX is looking into a divider where the opposite impedance is RL and the sum of the branch impedances is RL plus RF plus RS parallel 1 over SC plus R1. So that's the denominator, and the first factor represents how much of IX is going down RF. And I've already incorporated a definition of the corner frequency of the capacitor and R1. So the first factor gets us to the current down RF. The next thing I want to know is it's splitting again. I want to know how much current goes into the capacitor. Again, opposite branch RS divided by sum of branches, RS plus R1 with its corner frequency. So now we're at the current in R1. I multiply that by R1 to find VI. I multiply VI by all of this coefficient, and the result is IY. So that's everything. That's the loop gain. But it isn't, in fact, at pole zero form, because this corner frequency is buried in a couple of series parallel combinations. Also, notice I've dropped the RL because it's negligible compared to the RF. So there's using numerical values to justify an analytic approximation, because I'm leaving the rest of it in symbols. Again, subject to later review and correction if I'm going to change the values. Looks as though I'm not going to change them significantly to make any difference. Anyway, now we don't have the answer, in fact, at pole zero form. So we could do some algebra on this, which wouldn't be all that difficult, in order to put it into factored pole zero form. But there's a better way. One of the applications for the extra element theorem is, even when you know everything that's in the model, maybe you can simplify the analysis by dropping one of them out and putting it back in using the theorem, which is especially simple if the model is resistive and there's one reactive element, because then you get the corner frequencies directly. That's exactly what we have here. The calculation we've done involves only one reactance. So rather than doing the algebra to put this into factored pole zero form, let's simply drop the C to begin with by replacing it with a short. Obviously we choose a short this time and not an open, because if you take an open you're going to get 0 for the loop gain. So replace it with a short and find the mid-band value of the loop gain that results and call it Tm. At the same time, you can drop the explicit pole, omega A, which is part of the op-amp specification. So the mid-band value of loop gain is obtained by dropping the omega A and dropping the capacitor, which means dropping the other S terms as well. So now, we simply take the same answer and restrict it by dropping the S terms and calling the result Tm, mid-band value. This allows you to condense the result a little further into an even lower entropy form, which is this final result down here. Numerical value is 10 or 20 dB. Now we have to replace the capacitor. Again, we can do it all in our minds, applying the correction factor for the theorem. If we replace the capacitor with a second test signal, we have to calculate two driving point resistances, Rd and Rn. Rd is found by applying the test signal, single injection, and making the input 0. And here's this little catch again. What is the input? The input is the independent quantity in the denominator of the transfer function. The transfer function is t. The quantity in the denominator of t, don't have the right picture. The quantity in the denominator of the t is Ix, because t is Iy over Ix. In other words, Ix is the input signal for t. Vs is 0 at all times for this calculation. Vs is 0 to get t in the first place, and now we're doing some little sub-calculations to do with correcting t using the extra element theorem. So Vs is 0 to begin with, we don't even think about that. The input signal for t is the Ix. So the corner frequency for C in the pole is going to come from replacing C by the independent generator and finding Rd under the conditions that Ix is 0. So what's that going to be? Vs is already 0. If you look in place of the capacitor, you're going to see R1 to the right, plus to the left Rs, parallel Rf, plus RL. And there's no ambiguity at this point because Ix is 0, and Ix is the current in this path. So RL and RF are simply in parallel when Ix is 0. So that's the value of Rd. So that's going to determine the pole. The Rn is irrelevant. You can see that right off, because the C is a coupling capacitor in series with the signal path around the loop, just like the coupling capacitor was in the common emitter amplifier stage. So we know there is not going to be a zero resulting from the capacitor. But we can verify that by actually applying the theorem and calculating Rn. Because we replace the capacitor with the extra source, Vs remains 0, Ix is restored, and this time we null the Iy, because Iy is the output signal for T. If you null the Iy, it propagates back to 0 Vi. If there's 0 Vi, there's 0 current in R1, there's 0 current to the second source, and Rn is infinite. So it goes away. So the bottom line is you restore the frequency response for the loop gain by multiplying the midband value by the theorem correction factor for the series element. So the Z is 1 over Sc, the Zd is Rd, which we've calculated, the Zn is infinite, it goes away, and that leads to an inverted pole at omega 2. So we end up with a loop gain that has two poles, one of them normal and one of them inverted, and that's what the loop gain looks like. The magnitude asymptote graph for the loop gain has Tm of 20 dB mid-band, falls off above the normal pole at 2 kilohertz at the high end, falls off below the inverted pole of 30 hertz at the low end. So this is the first major result for the amplifier loop gain. And the next step is, now that we know what T is, we have to calculate, preferably graphically, because that's the easy way to do it. We'll see this time that the algebra is a lot more complicated, so the graphical construction to find the F and the D will be the easy way to do this. So this will show the power of the graphical method over and above the algebraic method. Well, we're talking about the analysis for the loop gain of an elementary little audio amplifier. This is the equivalent circuit model that we're working with, having stripped it down to the bare essentials. Notice that the forward path is now all the way down to an input voltage being applied to an infinite input impedance of the forward path, and the output of the forward path is represented only by this current generator. So you can't get much less in the model of the forward path. Everything else is external. What we've done so far is choose the point at the output of the final current generator to inject a test current in parallel for the purpose of calculating the loop gain. This sets up a current Ix that goes forward, and we followed it around the loop all the way back to the current generator, which is equivalent to the Iy, which comes back to the same point. And we've done the analysis for that using the extra element theorem as a shortcut along the way. The purpose of doing that was that if you put the capacitor in immediately, then you have some algebra to do to get the result, in fact, at pole zero form. Whereas by ignoring the capacitor, that is, replacing it by a short, we were able to get the mid-band value of the loop gain very easily, and then we restored the coupling capacitor using the extra element theorem, and that gives an inverted pole at 30 hertz at the bottom end of the mid-band loop gain, and then you restore at the same time the normal pole, which is part of the forward path, and that pole is at 2 kilohertz. So the result is that the loop gain has a mid-band value which is 20 dB, an inverted pole at 30 hertz, causing the gain to drop off below that, and a normal pole at 2 kilohertz. Gain drops off above that. So we've now arrived at the fundamental property of the feedback system, and the next step is to determine the derived quantities, namely F, the feedback factor, which is 1 plus T, and then the discrepancy factor, which is T over F. I'd like to leave you a few minutes now to do those steps. Principally the first one, the F, that's actually the more difficult one, because calculating F involves adding two pole zero functions. Even though the first one is only 1, then it still has to be added to the T, which is in fact at pole zero form. And so this requires the graphical construction that we've been talking about, and this is a little extension of the one we already did as the initial example, and so I'd like to leave you a few minutes now to do this. That is to construct on this graph, which is the t we have already, construct graphically the f, which is 1 plus t, and write the result in factored pole zero form. That means that you get the analytic form for the result, the quantitative result, but you do no algebra directly. Instead, you effectively do the algebra on the graph. So I'll leave you a few minutes to do that. Well, I'll go ahead with the construction now. Starting with the mid-band value, always the most important, of course, in this case. F is 1 plus t, so it'll just be a little bit bigger than the Tm. So this is Fm equals 1 plus Tm. When you get to the pole of t, the F is going to turn around at the same pole and is going to follow the same slope. And we've already done this part before, and we'll extrapolate that slope until you hit the final asymptote, which has to be 0 dB, because when t drops below 0, 1 plus t will simply become 1, and we've already done this part before and identified this corner frequency by gain bandwidth trade-off as Fm times the omega A. So that's exactly the same as we did in the previous example. The only difference this time is that we have something else going on in the lower part of the picture, but it's simply a reversed frequency direction, and the construction obviously will be exactly the same. So going down in frequency, the 1 plus t will have the same corner as the t, and that will continue parallel with the t until when the t drops below 0 dB, 1 plus t again will level off at unity or 0 dB, extrapolate the asymptotes as before, and label the intersection with the appropriate frequency using gain bandwidth trade-off again. Obviously this time we're going to refer this frequency back to the omega 2, where the gain was Fm, and now we want to find the frequency where the gain drops to 0 dB or unity. So this frequency is going to be omega 2 divided by 1 plus Tm, divided instead of multiplied. Or to be consistent, I can call this omega 2 over Fm. So the only difference, because of the reversed frequency direction, is you divide omega 2 by Fm, and clearly from the geometry you have to divide it in order to get a frequency that's lower. And that's all there is to the construction. Now it's simply a matter of looking at the blue graph and writing the factored pole zero form. Now you have 3 flat gains to choose from for the reference. And obviously it's the middle one that you're most interested in, so that's the one you should choose as the reference. So the solution to that will be F is equal to the mid-band value, which is Fm. Then you look up and down in frequency and see what happens. And as you look down in frequency, at first you're going to encounter a concave downwards corner. So that's an inverted pole at omega 2. As you continue to look down, you have a concave upwards corner. So that's an inverted 0. Now I could write this value out here, but instead I'll define a new frequency. I'll call this omega 3. So I'll write that as omega 3 over s. That's the inverted 0. And looking up in frequency, this is exactly the same as we had previously. There's a normal pole at omega a, 1 plus s over omega a, followed by a normal 0 at this frequency, and I'll define that as an omega 4. So that's a normal 0. So that's the factored pole zero format. And here's the neater version that's already been drawn. Same thing, where I've listed underneath the expression the definitions of the new corner frequencies that have shown up as part of the construction, which is a pair of zeros. And evaluating them numerically, the 0 at the bottom end is 2.7 hertz, the 0 at the top end is 22 kilohertz. So that's pretty straightforward. I kept emphasizing in anticipation of this particular problem that getting this result by the graphical construction is much easier than doing it algebraically when the t gets to be more complicated. Well, it's a little more complicated this time in the sense that t has two poles instead of the single one that we started with originally. So just to emphasize how much worse the algebra gets already for this case, let's see what would happen if you tried to find f algebraically. So here's the process. F is 1 plus t. So you substitute for the t that we have already. And the first thing you have to do is that since we had t with the form of the inverted pole at omega 2, the first thing you have to do is put it back into normal format with an s term on top. Then you have to cross multiply. Then you multiply out the factors in the numerator because there's an addition to do. And you collect the terms and you find that you have a new quadratic equation. And then if you resort to the conventional formula for the solution of the quadratic, this is what you have to substitute for the two roots in order to write the two factors of the numerator to find the two zeros. And you see what a ghastly mess that is. You have this whole long expression in the square bracket representing the new corner frequency that we found so easily. And even if you just define it and say as an omega z1, as I've done here, notice that what comes out of the algebra has unity coefficient in front with normal zeros and normal poles, so you've effectively chosen the zero frequency asymptote as reference, which is 0 dB. And who cares about that one? The Tm has vanished. The Fm has vanished. That's the important part. Now, of course, you could restore that by re-inverting the first pole and 0, and what comes out front then is the midband value of F, which is omega 2 divided by omega z1. Omega z1 is this mess in the square bracket. And you still don't get any useful interpretation of that in terms of the Tm. Now, you can rescue this by using the suggested new version of the quadratic solution, by going back to the previous step of the quadratic and following the recommendation, which is find out right away whether the q is high or low. And if it's low, then you can factor the quadratic into two real roots with a reasonable approximation. So the first thing to do is to look at the q of that quadratic, which is the coefficient of the middle term. And well, in terms of the A1, A2 coefficients that we've had before, the q is found in terms of those two coefficients, and this is what it is. And it's easy to see right away that it's a very small number, because it's the omega 2, which is 30 hertz, divided by omega A, which is 2 kilohertz, and then divided again by the square of the midband value of the F, which is 11. So the resulting number comes out to something very much smaller than 0.5 squared. So this validates the real root approximation extremely well. And the real root approximation that you're allowed to use now is the first factor of the quadratic is the same as the first two terms of the original quadratic, which is this. And then the second factor of the quadratic is the ratio of the third coefficient to the second one, which is this. So now we have the two real roots of the quadratic in a much simpler form than if you just plug directly into the conventional equation. But you still have a little more work to do to introduce reasonable approximations by noticing that the omega A term is negligible compared to the omega 2 term. And if you drop that out, you can reduce it down to something even simpler. And you still have to make the effort to re-invert the first pole and 0 in order to get the useful midband value as the leading coefficient. And if you do that, also leaving out the omega A terms, then eventually you can actually get it down to, can't get them both on together, eventually you can get it down to what you wrote in one line by taking the algebra off the graph. So there's a lot of things you have to work on and a lot of conscious choices you have to make in order to get the answer down to that simple and useful form. Already you see now the next most complicated case is if T has 3 poles, and then you might as well forget about doing it the algebraic way altogether. Okay, I should say one other point about this result. When we did this graphical construction, for the top part of the frequency response alone, just this part, we verified it on the spot by doing the algebra that this was the correct answer. By extrapolating these two asymptotes, that was the correct result for that corner. And it was exactly correct. Now, when we do it for this case, which has something else going on at lower frequencies, when you do it algebraically, you get the quadratic to factor, and we had to make an approximation, albeit a very good one, but still we had to make an approximation in order to get the same answer that we wrote down immediately using the graphical construction. This means there must be an implicit approximation in the graphical construction. So what is that approximation? Must be an approximation in this result, because when you do it algebraically, you have to make an approximation to get this simple result. So implicitly, you must have done the same thing by the graphical construction. The approximation is in assuming that there is no interaction between what goes on at the two ends of this picture. The algebraic approximation consisted in assuming that the two roots of the numerator quadratic, which are the omega 3 and the omega 4, are so far apart because the q is so small. But that is an approximation. So implicitly, we're doing the same thing graphically. We're assuming these two corner frequencies are so far apart that they don't interact. And it was such a good approximation that you don't even notice it. It was so obvious graphically. 2.7 hertz, 22 kilohertz. A long way apart. That's the big ratio that validates the Q factor of the quadratic being so small. So there's always a price you pay to simplify something, whether you do it graphically or otherwise. But the point is, the easier it is to see what the approximation is, the more likely you are to be able to incorporate it. So when you do this graphical construction, it's obvious without you even considering it, that the construction that you've done for the top end can simply be matched by the same construction at the other end, and they won't interact. notice that the non-interaction applies to the two zeros and not the two poles. There's no approximation to do with how far apart the two poles are. It's only the zeros, because they are the roots of the quadratic that you're approximating. Okay, that's really the crucial step, is in finding the f. The second question is the next step, which is now that we know t and f, we can find d, the discrepancy factor. And that's very straightforward, because now, once again, it is simply the difference between the red line and the blue line, because d is t over f, so midband d is tm over fm, and the construction at the top end is the same as it was before, so the d stays flat until the blue line levels off, then the d simply follows the original t. And the construction at the bottom end obviously is just the reverse. So d stays flat until you get to the frequency where the blue line levels off, and then d again follows the t downwards. And analytically, d is flat at the midband value, and it has an inverted pole at omega 3 and a normal pole at omega 4, which we've already defined in the previous step. Okay, this is the major part of the solution now. We've got the model, the AC model for the closed loop feedback system, injected a test signal, solved for the loop gain, and then determined the dependent quantities f and d. So we got one more principal quantity to determine, which is the g infinity, and then we'll put the g infinity together with the d, and that gives the final closed loop response. So to find g infinity, we go back to the model. And the procedure that we've established for finding g infinity is we can use the same model and the same injection point for a test signal, and we restore the original input voltage, and we use null double injection to determine the g infinity. So we've already chosen the injection point for the IZ. We restore the VS, and we twiddle the two knobs until we null the IY. And the reason we choose to do that is that if you null the IY, it propagates back to the input and nulls the error signal. And we know from the original definition that the nulled error signal is the condition under which we get the ideal closed loop gain g infinity, because it simulates infinite loop gain. So that's all you have to do. And here's your chance to practice doing a null double injection calculation again. What is it you want to find out? You want to find VL over VS under the condition that IY is nulled. The key to doing this in what looks like a different sort of circuit is simply to recognize that it's the identical problem to this one that we've already gone through. I talked about this already when I emphasized that the normal way that most people calculate the gain of this feedback system is to assume infinite loop gain, which is what allows you to say that the two inputs to the forward path are equal for zero error signal, and that's the condition you need to arrive at the result. And you see the model we're working with is identical to this block diagram. So follow the same argument. IY is nulled, so this generator is 0, so VI is 0. VI is the input to the forward path. That's the nulled error signal. If there's 0 voltage across R1, there is 0 current through it. Therefore 0 current through the capacitor also. Therefore 0 voltage at the feedback summing point. The only thing in the circuit we're talking about that's not present in the other one is this coupling capacitor in the R1. But the R1 is in the same position as the input impedance to the forward path. And I already emphasized when we talked about this previously that you make no assumption to do with the input impedance. It doesn't matter whether it's 1 megohm or 1 ohm. The null condition still means that if you have 0 voltage across it, you get 0 current into it. And it's the same thing here. You've got 0 voltage across a 2K resistor, but you still get 0 current in the resistor, therefore 0 current in the capacitor as well. So the feedback summing point is equivalent to the same summing point here, and it is a virtual ground. And so the RS is equivalent to the ZA. So the IA current, which is V1 over ZA, is the same as VS over RS. And the V2 over ZB, which is the IB current, is equivalent to VL over RF. In other words, the current down the RS all has to go through the RF because none of it goes into the C under this null condition. And all you do to find the G infinity is equate those two currents, which gives you the relationship between VL and VS, and it's just the ratio of RF to RS. So there's the condition. The null is propagated and you get a virtual ground at the feedback summing point. So the G infinity for this amplifier is RF over RS, which in this case is 1/2 or minus 6 dB. It doesn't matter, of course, that the gain is less than 1, because this is a voltage gain, whereas, of course, the purpose of the whole system is to be a power amplifier. Okay, that's the other part of the solution. You can see that's pretty simple. And the last step is just putting together the two pieces. The G infinity is constant at minus 6 dB, and the D we've already found, minus 1 dB with a pair of poles. So the actual closed loop gain is the product of the G infinity and the D, which is the direct addition on the dB graph. That gives you the green line. So the conclusion is the actual amplifier will give you a gain which is pretty close to the ideal value, the specification, over the frequency range, 2.7 hertz to 22 kilohertz, and beyond those limits, the actual gain will drop off, will deviate significantly from the G infinity. I've purposely chosen numbers that make this rather a poor amplifier, just so you can illustrate the relationships. And the deviation, even at best, is 1 dB away from the ideal value or the specification, because the mid-band loop gain wasn't that high anyway. It was only 20 dB. So Tm over 1 plus Tm is 10 over 11. So that's 10% less than 1, which is why you get a 1 dB discrepancy. There's an important conclusion to draw from this. The two corner frequencies of the actual closed loop gain, these two poles, are the quantities that have to meet your specifications, because your spec calls for a certain gain over a certain bandwidth. So those are the two numbers that you begin with for your design. They have to meet certain requirements. What are those two numbers? This is where the benefit of the design-oriented analysis comes in, because in order to get required values of those two corners, you're going to have to work back to what corners are required in the original circuit. Well, what are these corners? They're the omega 3 and the omega 4, which are the zeros of f, which are the roots of that quadratic equation. The messy ones. Those are the ones that determine the final result and whether or not you meet the specification. So they are the ones whose expressions you have to invert in order to work back from a known answer to what component values you have to use. So it turns out not only was it a useful analytic shortcut to do the algebra on the graph, but that is the crucial step you're going to need to do the design, to work that step backwards. And there's no way you can do it if you don't use the simplified roots of the quadratic. Okay, that's the end of the example showing how to use those methods in calculating the closed loop gain of the feedback system. And again, it's not just a matter of even doing the algebra. The important thing is that when you've done the algebra, you have to be able to invert it in order to do the design and change the numbers. Okay, the techniques we've talked about are how to determine loop gain by injecting a test signal into the closed loop instead of opening it. And there are two conditions that have to be satisfied in order to get the right answer. By doing that, you have to choose an injection point inside the loop, and it must be at a point where you don't upset the loading. Okay, we've kept talking all along about there being more than one transfer function that you need to know for a particular system. Although the most important one, and the one you do first, is usually the gain, as we've done for this audio amplifier. But there's also likely to be specifications on the input and output impedances. And we've talked about that a little bit, which is one reason why the input and output impedance theorem may be a useful thing. Because we don't want to have to repeat all of this work that we've done to find the voltage gain. And in this example, it's been a fair amount of work anyway, even using the shortcuts. So, especially in the case of an audio amplifier, there's going to be specs on the input and output impedances. Certainly the output impedance. The input impedance may not be so important. So now we have to go back and do a little more basic work on the effects of feedback upon input and output impedances. Now, everyone knows already from earlier background that feedback does affect input and output impedances. You may not have thought very hard about why that should be so. So, again, I always like to emphasize the motivation for doing something. So if we're going to look into the effect of feedback on impedances quantitatively, the first thing we ought to understand is why there is any effect anyway. So let's start with defining what an ideal amplifier is. And in terms of electronic signals, there's four possible combinations. You could have a voltage or current source, and you can have a voltage or current as an output quantity. So there's four combinations of those. The one we normally think of is the voltage-to-voltage amplifier. So what is an ideal voltage to voltage amplifier? It's one whose gain could be written on a spec sheet that is independent of the terminations that someone else may put on it. Specifically, you would like the voltage gain, Vs to Vl, to be independent of the source impedance and the load impedance. And there's only one way that can happen. The input impedance of your ideal amplifier would have to be infinite, and its output impedance would have to be zero. Otherwise, you would have a divider effect at one or both ends. And so the Zs and the Zl would get into the answer, and it wouldn't be ideal. So that's the definition of an ideal voltage to voltage amplifier. And likewise for the other ones. If the output signal is defined as a current IL, then you would want the gain IL over Vs, which is a transadmittance, to be independent of Zs and Zl. And again, the input impedance would have to be infinite, but this time the output impedance would have to be infinite also, in order for the output current to be independent of load. In other words, you'd need an ideal current generator at the output with infinite impedance. And, of course, the other two are simply the other combinations. If the input signal is defined as a current, Is, and the output is a voltage, then the ideal amplifier would have to have a zero input impedance. It would have to do current summing, in other words, and a zero output impedance. And finally, the ideal current-to-current amplifier would have to have zero input impedance and infinite output impedance. Okay, now, a real amplifier won't be ideal. So it will have a non-zero, non-infinite Zi, and it will have a non-zero, non-infinite Zo. So that in general, the gain is a function of the source and the load impedances. Now suppose you put some feedback around that amplifier. The basic property of feedback is it's going to transfer sensitivity of the closed loop gain from elements in the forward path to elements in the feedback path. And it's the first part of it that's significant here. In other words, the closed loop gain in the presence of feedback is going to be less dependent on the elements in the forward path. And the source and the load impedances are elements in the forward path, because they're part of the original gain. Therefore, if feedback is going to make the closed loop gain less sensitive to the source and load impedances, because they're in the forward path, there's only one way you can describe how that happens. The effective input and output impedances of the amplifier with feedback must have become more ideal, because that's the only way the result can be less sensitive to Zs and Zl. So that's the qualitative reason why feedback affects input and output impedances. So what's left now is to quantify that. Okay, the next thing is a non-ideal amplifier is non-ideal. That is, it doesn't meet any of the four limiting conditions. And you can't even say, except quantitatively, which one it might be closer to. But it's the way you connect the feedback that will determine in which direction the input and output impedances become more ideal. Because there's four different directions to go in. Input impedance could get more ideal by becoming infinite or by becoming zero, and the same with the output impedance. And it's how you connect the feedback that determines which direction it's going to go in at each end. Let's see how that works. Here's the original amplifier, non-ideal, and I've labeled the inside impedances and also the outside impedances. Now, we don't even have to say which ideal limit it's closest to begin with, because we're going to change it by feedback. What we do have to decide in advance is which limit we want it to approach. So let's take the most familiar one first. Let's suppose we want to apply feedback in the way that's going to make this non-ideal amplifier approach more closely the ideal voltage-to-voltage amplifier. That is, we want to raise its input impedance and we want to lower its output impedance. How are we going to connect the feedback path? So here's the feedback box, and I'm idealizing it. Now, how are we going to connect it? We want the closed-loop gain to be in the form of a voltage over a voltage, which means the G infinity must have the same dimensions. The G infinity must be a voltage over a voltage as well. That means the feedback path, which is K is the reciprocal of G infinity, so K must be the reciprocal voltage over voltage. That means you're going to have to connect the feedback path so that its input is the output voltage of the forward path, and it has to multiply it by K to produce a fed-back voltage. And the fed-back voltage has to be summed with the input, or actually it has to be differenced with the input in order to get the proper polarity. So that tells you right away how you have to connect this feedback path. You've got to connect it so that the voltage between the two input terminals of the feedback box are the same as the output voltage. So obviously you have to connect it in parallel with the output. And at the other end, the fed-back signal is a voltage, and you have to do voltage differencing with the input. And the way you do voltage differencing is by connecting in series opposition. So that tells you how you have to connect the feedback path at each end. So there's the same thing with the connection made. You connect the feedback box in parallel with the output, which you usually describe as sensing the output voltage. What you're really doing is choosing the output voltage to be the signal that is fed back. And then the feedback path converts it to a different voltage, which is then connected in series opposition in order to do the differencing. So what I've shown on here now is the closed loop impedances. So I put an extra subscript F on all four of those input and output impedances, indicating that feedback is going to change the effective values, and that's what we're now going to figure out. Quantitatively, what are the values of these closed loop input and output impedances? Okay, here's the derivation. All we have to do is use the output impedance theorem that says the outside output impedance, closed loop, can be found by using the theorem where the gain is the closed loop gain of the system. So here's the output impedance theorem we've set up already, and you apply it to the G. So the numerator is just the G itself. The denominator is G over ZL as ZL goes to 0, which of course is really just saying open circuit voltage over short circuit current. All you have to do is substitute the known relationship for the G in terms of the open loop quantities. So you could substitute A over 1 plus T in both places. But you can take the limit factor by factor. So G has two factors, A and 1 plus T. So I've separated the two factors, and you can take the limit independently. Then I've collected together the A from the numerator and the A over ZL with the limit from the denominator, and put that out front. Now, what is the significance of that group? It's the output impedance theorem applied to A. So it must be the original outside output impedance of the amplifier before feedback, which we've already labeled ZO prime. without the sub f. So that's the open loop outside output impedance before feedback. So that's what the A terms mean. So then you look at what's left. Well, here's T as ZL goes to 0. And that must be 0. Why? Because if you short the output, you kill the loop. Because the feedback box is connected right across it. So if you short the output, there is no feedback. You've killed it. So T goes to 0. And you're left just with the 1. Well, what else is left? Just the 1 plus T that came from the numerator. So that's the result. And it's a well-known result. You know it already. What it says is the outside output impedance of the amplifier with feedback is equal to the outside output impedance before feedback divided by the feedback factor. The same factor by which everything else gets changed. Okay, you know that already. Certainly it's lowered. It's made smaller by the feedback factor. You probably haven't seen the result derived quite so simply as that. That's the first answer. The second answer is, suppose you want to know what the inside output impedance is, ZOF without the prime. Well, you just take the other limit in the result you have already, same as we've been doing all along. So we take the result we have already, and it has two factors. So you take the other limit factor by factor, that is, you let ZL go to infinity. So that converts ZO prime to ZO. The original outside output impedance is converted to the original inside output impedance by letting ZL go to infinity. And in the denominator, you write T with ZL infinite. And you can't say any more about it than that without knowing in detail what's inside the T. But there's one thing you know about it. T with ZL infinite is bigger than T. Why? Because the loop gain is partially determined by the impedance divider between the ZO and the ZL, because that determines how much of the output signal of the forward path is actually applied to the feedback path. So if you let ZL go to infinity, that divider ratio rises to 1. But we don't know where it started, except it was less than 1. But when you let ZL go to infinity, it gets bigger. Therefore, the T gets bigger if you take that limit. You can't say how much bigger, but bigger. So the conclusion is the inside output impedance with feedback is equal to the inside output impedance before feedback divided by a factor which is bigger than F. You get a bigger reduction factor. That's not such a well-known result. Well, that's two answers in a very short space with very little algebra. But there's still something else worthwhile doing. Both of these results give the closed loop answer referred back to the open loop value. But we may not know what the open loop value is. And more than that, we don't care. All we care about is the closed loop value because that's what has to meet the specifications. So by exactly the same argument, which led us to abandon the A, because we don't care what the open loop gain is in the final result, by the same argument, we don't care what the open loop output impedances were either. So why not reformulate the result for the output impedances and avoid referring them back to the open loop values that we're not interested in? And so the trick to do that is, when you make, in the very first line, when you want to apply the output impedance theorem, instead of substituting for the closed loop gain G in terms of the open loop gain A, that's where the open loop values got back into it. Now we don't want to do that. So substitute for the G in terms of the new version, G infinity and T, which are the quantities we're interested in. So here's what happens when you make that substitution. Substitute for G in both places, G infinity times D. Separate the factors. G infinity cancels because G infinity does not contain ZL. Remember, any factor not containing ZL is unaffected by the limit and cancels out. So G infinity goes away. Remember, G infinity is determined by the feedback box only. It doesn't contain ZS and ZL. Okay, so collect what's left behind. And once again, we get a T with ZL 0, which is 0, and collect what's left, and this is the result. Now, you haven't seen that one before, I'm willing to bet. Looks a little mysterious, because it's got this funny limit still in it. But look at how useful that is, because it tells you that the closed loop output impedance of your feedback system is solely a property of its loop gain, and nothing else. That's sort of a revelation, I think. See, it doesn't matter what the open loop output impedances were, which is why you didn't bother knowing them. The loop gain alone determines the output impedance of your closed loop system. Which stacks up even more to the argument that the loop gain is the central important quantity. Because it's going to determine not only the closed loop gain, it's also going to determine the output impedances. Of course, the ZL is inside the T. So that's what enables you to evaluate this limit. Okay, now there's another little revelation too. You can go to the next line, as we did before, which is that you can also find the inside output impedance by the same substitution, or by simply taking the other limit in the answer we got already. So now, having found the outside closed loop output impedance, you can find the inside one by letting ZL go to infinity in the answer. So you write the first term with ZL go to infinity, and when you look at the second term, ZL is already limited out, so it doesn't change when you let ZL go to infinity. So that square bracket remains. So you find that the inside closed loop output impedance is also determined only by T. Well, that's not any new revelation after the first one. But the new information that you can get by looking at these two results is, what are the relative values of the outside and the inside output impedances that you can get by looking at these two results? Can you discern anything about the relative values? Remembering that T with ZL infinite is bigger than T. T is large already, mid-band. The two square brackets are the same. So all you have to compare is these coefficients in front. What can you tell about the relative values? Yeah, they're almost the same. Therefore, the inside and outside output impedances are almost the same. What does that say about the value of either one of them relative to ZL? Well, insensitive because of what value? Very low. They both must be much smaller than ZL for them to be almost equal, because the ZL in parallel is the only difference. Now that's sort of a minor revelation, perhaps. See, you couldn't tell that from the other two results, because you've got two things that are different in this formulation. But this formulation tells you right away that the output impedance, either one of them, is much less than the external load impedance. And it's not surprising, of course, because this connection of feedback is making the overall amplifier act more like an ideal voltage-to-voltage amplifier, which means its gain becomes insensitive to the load impedance, and the only way that can happen is for its effective output impedance to be much less than the load impedance. So everything fits together. Well, here we get 4 useful results, only one of which is well known and another one much less. The other 2 you probably haven't seen before at all, but very useful. Now here's just summarizing what those results are for this case. Now let's do the same thing for input impedance. We've already leaned on the duality more than once, and we're going to lean on it even more in the next few pictures. Suppose we want to know the outside input impedance of the amplifier with feedback. This is the formula we've already established. So all you do is substitute for G equals A over 1 plus T, take the limits factor by factor, group the A terms together, and identify them as the outside input impedance before feedback, Zi prime. Look at what's left. One of them is T as Zs goes to infinity, which must be 0. Because if you let Zs go to infinity, you're opening the voltage differencing loop and killing the loop again. So that must be 0. And all that's left is the 1 plus T. And you get the well-known result that series voltage feedback to the input raises the outside input impedance from its open loop value to its closed loop value by the feedback factor. If you want the inside input impedance, take the other limit in the result. That converts Zi prime to the inside value Zi, and it converts T to T with Zs goes to 0. And you can't say any more about it than that, other than T with Zs 0 is bigger than the original T. The argument is that there's a signal coming out of the feedback path, and what gets into the front end of the amplifier is determined by the impedance divider formed by Zs and Zi, which is a loss factor. Therefore, if Zs goes to 0, that loss factor rises to 1. So whatever value it started from, it gets bigger. So T with Zs 0 is bigger than the original T. So the inside input impedance with feedback is equal to its open loop value raised by a larger factor than F. However, who cares about what the open loop values were anyway? So make the the other substitution, which is go back to the first line and substitute G with G infinity times D. G infinity cancels because ZS is not inside G infinity either. Separate the other terms to find the limits, and this is the result you get, which says the input impedance with feedback is determined solely by the loop gain. And if you want the inside input impedance with feedback, take the other limit in the result, which means let ZS go to 0 in the first factor. It's already limited out of the square bracket, so that doesn't change. And the only difference between the two is the factor in front, both of which are almost 1. So the inside and outside input impedances are almost equal with feedback. Therefore, both of them must be much bigger than ZS. Which is consistent with the expectation that this connection of feedback raises the effective input impedance in order to make the overall voltage to voltage gain less sensitive to ZS. And the way it does it is by making the input impedances much bigger than ZS. So there's the words that summarize those useful things. Again, 4 useful results in a very small amount of algebra. One of which you knew already. The second one you may not have done. The third and fourth you probably didn't know at all. But very useful. This is a good example of high algebraic productivity. Lots of useful results with very little work. Okay, this is type 1 feedback. The connection that makes any old non-ideal amplifier behave more like an ideal voltage to voltage amplifier. Well, the next thing to go on to is the type 2 feedback connection. This time, the output signal is defined as a current, IL. The input signal remains a voltage. And the necessary configuration this time is you have to connect the feedback path in a different way. Because now G becomes a transadmittance. It's the output current divided by the input voltage, so G infinity has to have the same dimensions. So the K box has to have the reciprocal dimensions. So the K box is now a voltage over a current, which means the input signal to the K box has to be a current. So now you sense the output current IL by connecting the feedback box in series and sensing the current. The feedback box then converts that sensed current into a fedback voltage, which again is voltage differenced with the input signal by the series opposition connection. So this is the standard current sensing, and ideally you want to sense the current with a zero impedance. In practice, you do it by a very small resistance, an ohm or a fraction of an ohm, or you can do it by a current transformer. So the only difference is the nature of the feedback connection at the output, and now you can use the input and output impedance theorems again to find what the effect of feedback is. We have a little problem at this point, though. The output impedance theorem was set up on the assumption that the output signal was a voltage. So actually you need a different form of the theorem if the output signal is a current. But I purposely set up these drawings so that we don't have to go back and rederive a new theorem. we can set it up by direct analogy with what we've done already. Because notice that when we have this current sensing at the output, the configuration of the output circuit is identical to the configuration of the input circuit. So the new formula for the output impedance is exactly the same form as the theorem for input impedance, because the circuit configuration is the same. So all you have to do is take the same formula that we already have for input impedance and substitute the subscript, ZL instead of ZS. Because clearly, since the configuration is the same, the algebra will be the same as well. So the formula for the output impedance is the same as it is for input impedance, except for ZL in place of ZS for this configuration. Well, since the formula is the same, all of the things that we derive from it will be the same as well. So it's hardly even necessary to write it all out again, but I've done that anyway, just to be complete. The net result is the output impedance with feedback is bigger than the output impedance without feedback. And you get the same four results, and the same interpretation, of course, that goes with all of them. Okay? The input impedance formulas, of course, are identical to the ones that we've done already. Which is this. And in fact, I'm even using the same transparency, so I didn't have to draw it out again, but I reprinted it in the notes just so you'll have a complete set. But it's exactly the same as it was for the first configuration, because everything in the input circuit is the same. So again, series voltage feedback raises input impedances. So that takes care of case number 2. Well, there's 2 more cases which we can go through with monotonically increasing speed. Because there's less and less new each time. So type 3 feedback, the output is back to the original configuration because the output signal is a voltage again. But this time the input signal is going to be a current instead of a voltage. So the requirement is G is a voltage over a current, namely a transimpedance. So the G infinity must be a transimpedance. So the K must be a transadmittance, upside down. So the K box has to sense the output voltage and convert it into a fed-back current. So we have to do current differencing at the front end, which is done by shunt opposition connection. That is, some of the input signal current is diverted into the feedback path, leaving an error current to go into the front end of the amplifier. So it's just the dual of the previous configuration. All right, what about input and output impedances? Well, the output part of it is back exactly as it was in case 1. So the formulas for the impedance are exactly the same. And again, if I can find it, I can use exactly the same overlay. So there's the first one we have. Voltage feedback lowers output impedances. Okay, now what about input impedances? Now, once again, the input impedance formula was derived on the assumption that the input signal was a voltage, and now it's a current, so we need a new formula. But now, obviously, we do just the opposite from what we did at the output, because I've carefully drawn the configuration now to show that the input circuit is identical with the output circuit. So the new formula that we need for the input impedance is exactly the same format as the original formula for output impedance, except we substitute ZS for ZL. and all the corresponding results are the same. Namely, shunt opposition feedback or shunt current feedback lowers input impedances. So that's type 3. And finally, type 4, there's nothing new at all. Type 4 is current to current. So again, we have to sense output current and convert it to a fed-back current by shunt opposition connection. And the appropriate formulas are, for output impedance, it's the new version, like the input impedance was originally, with ZL substituted for ZS. Same overlay. And the input impedance is also the new one, which is like the output impedance, except ZS substituted for ZL. So you get a symmetrical relationship between all of these quantities. Okay, so much for setting up the basic relationships to do with the effect of feedback on input and output impedances. So now we can go back to that audio power amplifier example and see how that works out as applied to that particular circuit configuration. The first thing to notice is, this is the model we've had already. First thing to do is identify which of the 4 types of feedback this is. And it's type 3, because the feedback path, which is simply the resistor RF, senses the output voltage because it's connected in parallel with the output, like type 1, but at the input it's a shunt opposition connection. So the real input signal is a current, and this is a type 3 feedback system, in spite of the fact that I've drawn the source as a voltage Vs. Because I can convert Vs in series with Rs to a Norton equivalent of Is in parallel with Rs, and by definition those are equivalent, which would be this. And you see that what determines which of the 4 types the system is not how you identify the source or the load. What makes the difference is how you connected the feedback. So regardless of whether I use Is as the explicit source or whether I use the Vs, which is what I in fact did, regardless, it doesn't change the fact that this is a type 3 feedback system, because I'm not changing the connection of the feedback when I change the representation of the source. And the consequence is, since it's type 3, the feedback lowers the output impedance, and it also lowers the input impedance. Because that's the consequence of the shunt opposition connection at the input, regardless of what I've defined as the source. Okay, let's calculate now the inside output impedance. Inside output impedance is the only one that matters in this case. Outside output impedance is of no interest because nothing else is going to be connected beyond the loudspeaker. So usually the audio amplifier is specified separately from its load. So it's the inside output impedance that would appear on the data sheet. So let's calculate ZOF. So back to the model. Let's use the version which refers back to the loop gain only, since we don't care what the open loop value was anyway. So All we need to substitute in this is the loop gain expression, which we've set up, and I've summarized it again down below. It has a mid-band value, and it has two poles. So all you have to do is evaluate this limit and the factor in front. So let's evaluate the limit with RL going to 0. So I have to take RL over T. So that's RL over Tm. And the Tm is proportional to RL, so it will cancel. And then I have the two corner frequencies for the T, and the two poles of T will be zeros of this function. And I look at the two poles, and the omega A does not contain RL because it was a fixed parameter to begin with, and the omega 2 does not contain RL either. So there's nothing left in that expression that has RL in it, so taking the limit doesn't make any difference. So that's all you get for the square bracket. This is the result. Now you work on the other factor. T over 1 plus T as RL goes to infinity. Again, the Tm is directly proportional to RL, so if you let RL go to infinity, T goes to infinity and that factor goes to 1. So the square bracket we already calculated is everything that's left. So the coefficient in front has dimensions of resistance, so we call it the mid-band value of the output resistance with feedback, ROF, and there it is, and it has two corner frequencies, an inverted 0 and a normal 0, which are the same frequencies that were originally in the T. Numerically, the ROF is 1.5 ohms. And then the zeros outside that range cause the closed loop output impedance to rise. Okay. Relate this to what you expect. The mid-band output resistance is very small. It's 1/10 of the load resistance, as a result of the fact that inside and outside output impedances both will be much lower than the load itself. However, it's only low over a relatively narrow frequency range. And it rises when the loop gain starts to fall. Notice the closed loop gain was flat from 2.7 hertz to 22 kilohertz. But the output impedance is only low over the much narrower range over which T is large. Okay, now let's go back and check this result with what we would expect from looking at the diagram itself. Consider very low and very high frequencies, which means the loop gain has gone away and the system is effectively operating open loop. Look in at the output to the left of RL, that's the ZOF that we're calculating. What would we expect the result to be at very low frequencies? Well, this current generator would be inactive at very low frequencies because when we apply the test signal at the output in order to determine the output impedance, the Vs would be 0 and the test signal we apply would go down the feedback path, but this coupling capacitor would be open at very low frequencies, so there wouldn't be any Vi, so this generator would not be activated. So the only contribution to the 0 frequency output impedance is the impedance of the feedback path itself plus Rs, the capacitor being open. So the 0 frequency asymptote of the output impedance ought to be RF plus Rs, or 3K. That's not what the calculation showed, though. Calculation showed the result going to infinity at 0 frequency. So something's wrong. Likewise, at infinite frequency, if you apply a test signal at the output, the signal would go down the feedback path and the coupling capacitor would now be a short, so you'd get a non-zero VI which would activate this generator, except for the fact that at infinite frequency the pole would cause the generator to be zero again. That's why you get zero loop gain at infinite frequency as well. So once again, the only contribution to output impedance at infinite frequency would be the impedance of the feedback path itself plus RS parallel R1, because the coupling cap would be a short, which would be 1K plus 2 parallel 2, or 2K. So the output impedance ought to be flat at 2K at infinite frequency. And again, the analytic result didn't show that. It showed it going to infinity. So at both ends, we're getting the wrong answer somehow. So what went wrong? That we now have to track down the source of a discrepancy. The answer doesn't agree with the prediction. In this case, the answer was checked not experimentally, but by simply going back and looking at the model and figuring directly what ought to happen at certain extremes. So we can't blame the model, because the discrepancy comes from two answers to the same model. So the only discrepancy can be somewhere in the derivation of this predicted answer. So assuming we didn't actually make a mistake, we must have made an approximation somewhere that has turned out to be invalid. Can you remember what that was? Well, if you look back through the notes, you see any approximation that was made, I think, was indicated explicitly. And here it is. The very first line when we wrote down the loop gain by injection of the IZ. There it is. Dropped the RL. For the very good reason that RL is 15 ohms compared to RF, which is 1K. And I mentioned at the time, that's a very good approximation. And even though we're sticking our necks out by saying that we may want to change values later, it's not likely that we're going to invalidate that approximation. But something else happened to invalidate that approximation. You see what that was? How did we evaluate the output impedance? We used a formula that required us to let RL go to infinity. If we've already dropped RL compared to something else added to it, we're not allowed to let it go to infinity. That invalidates the approximation. So I've purposely gone through all that as a reminder that you do have a price to pay for using simple methods and shortcuts and all that, which is back to what the mathematicians, of course, have warned us about all along, which they say is a good reason not for making approximations that you can't justify immediately. And I've been telling you the opposite. Go ahead and make those approximations anyway, and you have to go back and check, and you can't lose by trying. So I purposely put this in as a reminder that you do have to do that. But anyway, I still claim you can't lose by trying, because having determined now that this answer was wrong, at the two extremes because of letting RL go to infinity. The next question is, what are you going to do about it? And so the hard thing to do is to go back to that very first line of the derivation and not leave out the RL. And then you could work through again to the answer. That's equivalent to going back to where you made the approximation and then not making it, which is no worse than if you had done that in the first place. But that I still say that it isn't even necessary to do that, because the way in which we detected the error was by figuring out what the answer ought to be at those extremes. So why not just put that in as a correction at the end? Because we know what these flat values ought to be. And by gain bandwidth trade-off, you can determine where this corner frequency is, which is 15 millihertz. You could put those flat values in, and you get 15 millihertz for where this asymptote ought to level off at the value we expect. And at the other end, it ought to level off at a different value, and that would occur at 2.7 megahertz. So we've fixed up the answer anyway, and the bottom line conclusion is we don't care anyway. We don't care what happens at 15 millihertz or 2.7 megahertz, because we know very well that the basic model we started with has fallen apart long before you get to those frequencies anyway. Remember, we've included an output power transformer and modeled it with the turns ratio of n. And the transformer certainly is not going to have a conversion ratio of n at 15 millihertz or 2.7 megahertz. So besides the fact that we don't care what happens there, the model isn't right anyway. So there's absolutely no point in going back and correcting that analysis in order to get this refined answer. So there's another example of don't do any more than you have to. So it was certainly worth making that approximation to begin with. And even though at the end we found that it was invalidated, at the same time we can show that we don't care anyway. Okay, now another comment about the output impedance. It's very low, but only over a pretty narrow range, which means the damping factor for the loudspeaker, which is part of the design criteria, is not so good when you start getting outside that range. The design of a speaker is sort of a special case of a load. It's a pretty complicated electromechanical system on its own. I'm sure you know a lot about that already. If the speaker designer designs the speaker to be driven from a low impedance source in order to get a high damping factor. Damping factor is simply the ratio of the speaker impedance to the source impedance. A damping factor of at least 10 is usually specified. The reason that the loudspeaker manufacturer says you ought to use that low output impedance is he's counting on it to damp the basic mechanical resonance, which is formed by the mass of the voice coil and the cone and the compliance of the suspension. It's a real mechanical resonance, usually down around 100 hertz or less, and the bigger the speaker is, the lower that frequency is. If you don't damp it, then you get an excitation of that resonance regardless of what the audio signal is. I always refer to that as the jukebox effect, because somehow jukebox manufacturers seem to design them that way on purpose. But it doesn't matter what note of music is being played, the only thing you hear is that thump. And when I talked about this in my class at Caltech years ago, I used to have a demonstration of this, we had a 15-inch speaker in a bass reflex cabinet that was reasonable. And I rigged up a little power amplifier that had an A-B switch on it, and I could go back and forth between high output impedance and low impedance, and yet keep the overall volume level about the same. So the only difference was the damping factor. So I'd bring in a little tape of some of my favorite music, like Count Basie or something, and I'd play this stuff, and I'd turn the switch A-B. And I did that for a few years, but then I found out that they usually liked the lousy ones. So I gave up that demonstration. We had to make another change too. We have a senior project lab where we try to simulate the real life situation to some extent by making them write a proposal and establish specifications, and then they had a term where they had a budget also, both of money and time to do this, and then at the end of the term they had to demonstrate that their project worked and met the specs. It's quite a good idea, but we got people who were submitting proposals to make guitar fuzz amplifiers whose objective is to increase the distortion. Yeah. And they didn't want to specify the increased distortion, they just wanted to maximize it. So we decided that wasn't an acceptable project proposal. But, we keep fighting these rearguard actions, you see. But anyway, we have to change the examples of these things as we go along too. Okay, back to this one. I'll indicate, and I've got the full solution in the notes for you to look at also, the application of the input impedance formula. Suppose you wanted the input impedance, not that it's of any great significance in this case, especially as it's going to be low because of the shunt feedback. But if you used the formula for input impedance, this is what happens. Again, you simply have to know what T is, so I've listed here what T is with the various parameters. And then you have to evaluate these limits. And the algebra is quite a bit longer this time. You've got to go through this. I won't go through the detail. You can follow it if you like. You go through this whole page and on to the next page. And the reason it's so much longer is that the RS shows up in the T in more places. It's in the TM, it's in the omega 3, and it's in the omega 2 as well as the TM. It's also in the omega 4 because of the TM. So the RS is sort of littered over a whole lot of different places. So when you take the limit, you have more work to do. So I won't bother with the details, but this is the result. It's a mid-band value, which is low, as expected, because it's shunt feedback. And it rises outside the range where the loop gain starts to go away, and it does level off at both ends. So it's got 2 poles and 2 zeros, and it's a more complicated result than the output impedance was. And the reason for that is that we did not make any approximation at the beginning to do with RS. We didn't leave RS out anywhere. And that's why the analysis is more complicated, and that's why the result is more complicated. We didn't make any approximation. And you see, you get the 2 flat values at the 2 extremes. Okay, well, won't say any more about it because it's not a very interesting result anyway. Okay, let's do one more thing regarding distortion. This is just an example of how you can go about calculating the effect of feedback on distortion. You have to have a reference condition. This is why earlier on I talked about the interference to output transfer function. This is where we're going to use that. You have to know where you start. That is, how much distortion is actually generated in the power output stage. That's where most of it comes from, because that's where the signal amplitude is largest, and therefore the nonlinearity of the characteristic is worst, because you're exercising the operating point over essentially the full range. So let's suppose, just to pick a starting point, when you drive this little power amplifier to maximum output at 1 kilohertz, for example, let's suppose that it develops 3% second harmonic and 5% third, which you could find out just by measuring it with a wave analyzer or distortion meter. So that's the reference condition. The only thing to find out is, if this is what it develops, measured open loop, what do you get in the presence of the closed loop feedback? You have to compare the same reference condition. That is, you have to compare the condition when the output is still being driven to the full level, the same level at which you measured the open loop distortion. That's the only way you get the same distortion generation, and then you find out how much the feedback reduces it. So all you have to do is use the result that we set up before, that feedback reduces the distortion to output transfer function by the amount of feedback. And all you have to do is evaluate the amount of feedback at each harmonic frequency. So this is what the feedback factor is. Feedback factor is F, 1 plus T. And we've already gone through the graphical construction and written the factored pole zero form for F. So we have this result already. Now we're talking about the case where the fundamental is at 1 kilohertz, therefore the second harmonic is at 2, the third harmonic is at 3. So right away, we don't need to know anything about the pole of T, which is at 30 hertz. So ignore it. Don't put it into the problem. It's not necessary. All we have to do is evaluate 1 plus T at the second harmonic of 2 kilohertz and at the third harmonic of 3 kilohertz. That's all you have to do. So when I say you evaluate the F, what I mean is you find the magnitude of F at the second harmonic frequency of 2 kilohertz. So here's F, or 1 plus T, which is the flat value with the pole at 2 kilohertz. So the magnitude of that is 1 over the square root of the sum of the squares of the real and imaginary part evaluated at the second harmonic of 2 kilohertz. And that happens to be the same as the corner frequency. So the result is 1 over the root of 1 plus 1, or 1 over root 2, which is the 3 dB down point, of course. So the flat value is 11. Divide that by root 2, and the answer is 7.8. So that's the magnitude of F at the second harmonic frequency. Then you do the same for the third harmonic. Evaluate the magnitude of F at 3 kilohertz, so that's 1 over the root 1 plus 3 over 2 squared, which comes to 6.1. So that's the reduction factor for the third harmonic. And then the definition of total harmonic distortion, THD, is the RMS combination of all of the harmonics that are present. The RMS combination is the root of the sum of the squares. So in this case, we only have 2 harmonics specified. So the second harmonic originally was 3%. Now it's going to be divided by F at 2 kilohertz, which is 7.8. Then you square that. And then the third harmonic was originally 5%. That gets divided by 6.1. Square that. Add it to the first one. Take the square root, and the result is a little under 1% THD. And once again, notice that in spite of the fact that the closed-loop gain bandwidth is flat from 2.7 hertz to 22 kilohertz, it's still a crummy little amplifier. Because not only does the output impedance rise outside the much narrower mid-band range for TM, but the distortion reduction factors also decline outside the same narrow range. In other words, the reduction factor for the third harmonic is already little more than half what it was at mid-band, at 3 kilohertz, because the loop gain is dropping off well within the flat bandwidth of the overall voltage gain. So the conclusion from that is, which I'm sure you know already, in order to make a respectable feedback amplifier, you have to keep the loop gain itself high over the entire range over which you want to get the benefit of the feedback reduction factors, which means you want to keep a high loop gain of 20 dB at least, not from 30 hertz to 2 kilohertz as it is in this example, but you want to keep it high over the range maybe 20 hertz to 20 kilohertz. And 20 dB isn't much either. What if you make it 40 dB? You've got to keep it at 40 dB between 20 hertz and 20 kilohertz. Now you see the design problem is getting a good bit stickier. But that's what you have to do if you really want to make a decent feedback amplifier. And I'll come back a little later and say some more about that, to do with the squeeze that you get in and what you can do about it. Okay, summarize where we are on this. The effect of feedback on impedances. Output impedance is decreased by voltage feedback and increased by current feedback. It's only the connection at the output that makes the difference as to which way it goes. Likewise, the input impedance is increased by series feedback and decreased by shunt feedback. And again, it's only affected by the way you connect the feedback at the input. What you do at the output makes no difference to the input impedance, and vice versa. Outside impedances are changed by the regular feedback factor. Inside impedances are changed by a larger factor, and you also have a whole set of alternative formulas which allow you to find the impedances directly from the loop gain without going back to the open loop values. So that's the end of that section. So far we've talked about several things to do with feedback, all of the good things. Now we've got to talk about the price you pay to get those benefits, namely the possibility of instability. The nemesis that Harold Black's supervisors had warned about from the start. And Black, of course, recognized that and took the positive attitude that we could do something about it. So that's the part of the problem we have to talk about now. Okay, first we have to define what stability is. The closed-loop gain of a system can be represented in factored pole zero form. The poles are the roots of the polynomial in complex frequency that appears in the denominator. So you may have linear roots or quadratic roots or whatever, but there's a polynomial in complex frequency in the denominator. And the stability requirement is that all of those roots be in the left half of the complex plane. That is, they should have negative real parts. And the simple interpretation of that is that you can express this factored pole zero form of the closed loop gain as the sum of partial fractions. Remember partial fractions. Whenever you have a series of factors multiplied together in the denominator, you can separate it into the sum of factors where each one has the denominator of one of those roots. So you can basically divide the function into the sum of factors of the form 1 over 1 plus s, plus another of the form 1 over 1 plus s, and so on, however many roots there are. Now, the stability requirement is that the roots should be 1 plus s in the denominator and not 1 minus s. That's what you mean by saying that the root s has to have a negative real part if it's the solution of 1 plus s. And the reason that's necessary is that if you take the inverse Laplace transform of 1 over 1 plus s, the result is e to the minus t. And it's the minus that's important, because e to the minus t is a decaying exponential. That's what you mean by stability. On the other hand, the inverse transform of 1 over 1 minus s is e to the plus t. And that's a rising exponential. That's an instability. So it's easy to see why all of the roots of the denominator have to be 1 plus s and not 1 minus s. So that's basically the stability requirement. Notice there is no requirement on the zeros. You can have right half plane zeros of the form 1 minus s, and the system is still stable. That's why when we talked about right half plane roots, it's okay for zeros, it's not okay for poles. So that's the basic definition of stability. Now let's relate that to a feedback system. The closed loop gain can be written as the open loop gain divided by 1 plus t. The open loop gain itself can be written in factored pole zero form. Notice that the poles of A are also poles of G, because anything in the denominator of A is also in the denominator of G. So let's take the simple case where we assume that the open loop amplifier is stable. That is, all of the poles of A are in the left half plane. They're all of the form 1 plus s. Notice we adopt that as a restriction. It's not necessarily true. It is possible to have an open loop unstable amplifier and yet stabilize it when you close a loop around it. But that's a pretty tricky thing to do. So let's not get involved with that esoteric case. So let's make the usual simplifying assumption that the open loop amplifier itself is stable. You might say that's not much of an assumption, because if by definition it doesn't have any feedback, how could it be unstable? Well, that's true, but you have to remember that there's all sorts of feedback effects which are inherent in your amplifier that you may not have put there on purpose, because there's things that you can't control. For example, even inside each transistor, that collector-based capacitance is in a feedback position. And there may be other internal feedback loops that are unintentional, but you're stuck with them anyway. So in fact, it does require a separate independent assumption that the open loop amplifier itself is stable. So the zeros of A don't matter, whether they're right or left half plane. So if we impose the condition that A itself has only left half plane poles, then we can dispose of A from further consideration. And the only thing left that determines the stability of the closed loop feedback amplifier is the zeros of F. F is 1 plus T. F is in the denominator, so the zeros of F are the poles of G. So the stability requirement is that the roots of F, which are at zeros, should all be in the left half of the complex plane. Now, Nyquist's name is usually associated with the stability criterion, and what Nyquist did was he translated that condition. F has no roots in the right half plane. He translated that condition into an equivalent condition that says if you make a polar plot of F, a polar plot means that you draw a graph of f as a function of frequency using the length of the phasor representing its magnitude and its angle being the angle of f. And you trace out this contour as a function of frequency, and you get a closed contour as a result. And what Nyquist did was show that if that closed contour for f does not encircle the origin of the polar plot, this is equivalent to saying that there are no roots in the right half plane. Now, it takes some complex variable theory to derive that relationship, and this is the standard bookwork that you find in the books to do with Nyquist stability criterion. So I won't go through that derivation. Usually there's one further step. Because f is actually a derived quantity, t is really the fundamental quantity, usually that result is also translated to say if the contour of f does not encircle the origin, since f is simply 1 plus t, there's a unit shift. And the equivalent condition is that the polar plot of t should not encircle the -1 point. That's obviously the same thing, just shifting the effective origin by 1 unit. And it's in that form that you normally see the Nyquist stability criterion. The polar plot of t must not encircle the -1 point. So that's in all the books. What you don't find in so many books is what polar plots really look like for some useful cases. So let's talk about that. Let's take the simplest form of loop gain, which is a flat value t0 and a single pole. The way you make the polar plot is you start with 0 frequency, t equals t0, so you draw a phasor length t0 at 0 degrees to the reference direction. And you label the end of it omega equals 0. Then you take a higher frequency and find the magnitude of t, which is now a little less than t0, and it starts to build up a lagging phase angle. So you mark the end of that one with some arbitrary value of frequency. The first one of any particular interest is the corner frequency itself. If you put s equals j omega 1, the magnitude is down to 1 over root 2 t0. And the angle is now 45 degrees. And then beyond that, the magnitude gets smaller and the phase angle approaches asymptotically 90 degrees. So eventually, at infinite frequency, the magnitude is 0 and the phase angle is 90 degrees. Now, again, if you dust off a little of your high school geometry, you may recognize that the shape of that contour is a semicircle. Take the particular case at the corner frequency. The length of the phasor is t0 over root 2. The diameter of a circle subtends a right angle at the circumference. And the other chord is 1 over root 2 times t0 also. Whatever, I'm sure you're willing to accept the result that the shape of the contour is a semicircle. Now, Nyquist said we have to draw the contour not only from frequency 0 to infinity, but also from minus infinity to 0. And that's easy, because the only difference is the phase angle is reversed for negative frequencies. Magnitude stays the same. So the negative frequency contour is simply the vertical inversion of the positive frequency shape, and since that was a semicircle, the full contour is a full circle in this case. The negative frequencies, of course, is what closes it. So Nyquist criterion says that the closed contour must not encircle the -1 point. And so when you look at this result, the answer is it does not encircle the -1 point, and moreover, it never will, regardless of the values of the parameters. Because changing t0 or omega 1 simply changes the scale of the circle, but it will always remain on the right-hand side of the origin, and it will never get to -1. So the conclusion is a single pole loop gain is always stable. So that's the base comparison position. So the next most interesting case is two poles. So you start out at zero frequency the same way on a semicircle, but then as you get close to the second pole, the magnitude will go down faster and the phase angle will increase faster, and you'll eventually go to an infinite frequency at zero magnitude with a phase angle of 180 degrees. And then you have the vertical inversion of that also that closes the contour, and you look at it and you say, does it go around -1? And the answer again is, no it doesn't, and it never will. It could get very close to it, but it will never get to the -1 point, because that would require the magnitude to be finite and the phase angle to be 180, but with two poles you don't get to 180 until infinite frequency when the magnitude is 0. So still, a two-pole loop gain is always stable. It's when you get to three poles and up that you have possible problems. Take the smallest of these contours. This is three poles now because you end up at infinite frequency with zero magnitude, but from the 270 degree direction, 90 degrees from each of the three poles. And the answer now to the stability question is, well, it could be stable or not depending on the size of the contour. The smallest one is stable because it doesn't go around -1, but the next one out, which is basically the same shape, is unstable because it's bigger and it does go around the -1 point. So the conclusion is that a three-pole and up system is stable or unstable depending on the particular values involved, and typically would be stable for low values of gain and might go unstable for higher values, since higher values of the T0 or whatever the parameters are of the loop gain, higher values of the parameter obviously make the contour get bigger. So typically a three-pole or up system might be stable for low values of loop gain, but might go unstable at higher values. There's no point in looking at four poles or higher, because obviously there's just more variables involved, and you have the same conclusion. It could be stable or unstable depending on the numbers. But there is a third contour here, which is a sort of pathological one. According to Nyquist, it's stable, because it doesn't go around the -1 point, but it has the peculiar property that the phase angle has actually increased beyond 180 degrees, while the magnitude is bigger than 1. But what saves it and makes it stable is that the phase comes back below 180, and when the magnitude is going through 1, the phase angle is below 180, which is what makes the contour avoid the -1 point. So that's known as a conditionally stable system. And that may be all right, but the problem with it is that if it's stable under a normal configuration, such as the one I've shown here, it could go unstable at lower values of gain, because a lower gain would make the contour get smaller, and if it gets smaller in such a way that this loop went around -1, it would go unstable at a smaller scale. Now that's hazardous, because you can visualize a whole lot of abnormal conditions, or maybe not so abnormal even. Because suppose you've designed a conditionally stable feedback system, and you've checked this criterion and it's fine, everything's okay. But the first thing you have to do with it is switch it on. Now before you switch it on, everything is quiescent. The gain is 0, which means this contour has collapsed to a point at the origin. Then you turn on the power, and then the coupling bypass capacitors charge up and you have a turn-on transient. And the gain gradually builds up, so the contour starts expanding from the point of the origin, and it expands, not necessarily keeping the same shape, probably won't, But anyway, it expands in some way towards its final conditionally stable configuration, the one that is stable. But you see, the hazards of ensuring that it doesn't go around the -1 point somewhere on the way up is a pretty difficult proposition. Now, you might be lucky. Even if it goes around the -1 point on the way up, that might mean you get a temporary oscillation during the turn-on transient. If you're unlucky, it could get stuck. Because when it oscillates, the amplitude builds up until something limits and goes nonlinear and prevents the gain from rising anymore. So it could get locked up in the unstable condition and never get to the final conditionally stable position. And that's only one of the possibilities, because suppose you survived that and it did finally come up to the conditionally stable system and everything is fine, but then someone comes along and hits the output with an overload. Again, something saturates, cuts off, the gain drops. And the contour contracts, and again, it's going to be very difficult to ensure that it doesn't contract in such a way that it could go unstable again during the overload. And you could also be unlucky and it could get stuck in the overload condition. Even if you remove the overload, it may not recover because it's already oscillating and going nonlinear. So you see, there's all sorts of hazards in a conditionally stable system, mostly to do with abnormal conditions. But to try to anticipate all those possibilities is a pretty tough thing to do. So the basic conclusion is, don't design a conditionally stable system unless you really have to. Stay away from it. So let's go on to the next point, which is, now we want to have a stable system, and we want to have some degree of measurement of how stable is it. So I've drawn here an arbitrary stable contour that doesn't go around the -1 point, and there are a couple of standard definitions of degree of stability which are related to how close does the contour get to -1, which is the critical point. So the first standard definition is, you draw a unit circle around the origin and you find the point where the contour crosses that unit circle. That frequency, of course, is the crossover frequency. It's where the magnitude of the loop gain is 1. Now, at that frequency, the phase lag will be less than 180 degrees. And how much less it is by definition the phase margin. If the phase margin goes to 0, you're on the brink of instability because the contour is right next to the -1 point. The formal definition is phase margin is 180 degrees plus the angle of t evaluated at the frequency where the magnitude of t is 1, or 0 dB. Remembering that the angle of t is negative because it's a phase lag, means that the phase margin is a number less than 180 degrees. And it had better be more than 0 if it's going to be stable. That's a standard definition. There's another standard definition, which is, if you go to higher frequencies, eventually the phase lag may get to 180, but by then the magnitude is less than 1, and how much less than 1 it is by definition the gain margin. The formal definition is the gain margin is specified in dB, and it's given as a positive number of dB, which means it's defined as the negative of the magnitude of t in dB evaluated at the frequency where the angle of t gets to -180. And since the magnitude of t is less than 1, it's a negative number, and the minus in front converts the result to a positive number, which is the way you specify gain margin. So those are standard definitions. And here's the same thing on the more conventional Bode plot, which is the plots we've been using all the time, which is separate graphs of magnitude and phase versus frequency. So here's the identification of those margins on this picture. You find the crossover frequency, which is where the magnitude is 1, and you look down to the phase graph, and how many degrees less than 180 it is the phase margin. And then you find the frequency higher up where the phase may get to 180. And you look back at the magnitude graph, and how many dB below 0 it is the gain margin. Now, why are there two definitions of stability? Because neither one of them is very good. If you go back to this case, it's easy to visualize another sort of pathological case where the contour might look like this. It's stable. It has the same phase and gain margins as the original contour. But you certainly wouldn't consider it to be equally stable. Because obviously the closeness of the approach to the -1 point is of some concern. So those definitions of margins are not complete. You could think of a better one. Since the closeness of the contour to the -1 point is really what you're interested in, you could invent another definition which would involve drawing another circle centered on -1, and you draw as big a one as you can tangential to the actual contour. And then you would define the radius of that circle as a stability margin, and you would like it to be as large as possible. And then that would take care of that pathological case. So this would be a better definition of degree of stability. The trouble is, it's a lot harder to calculate it. And the only reason I can think of why it isn't used is that reason. Anyway, we have to go back and deal with the conventional ones. Okay, now I mentioned a few minutes ago when I was talking about the case, the conditionally stable case, and I suggested don't design a conditionally stable amplifier unless you really have to. And I thought someone might have asked, why might you really have to? So let's talk about that for a moment. It may be the only way that you can design a system and keep within narrow windows of specification. So I can use this for a couple of examples. It's set up for an example of a switching power supply, but it's also set up for an example to do with an audio feedback amplifier. So since you're probably closer to that one, I'll use that example. I already led into it a little earlier on by saying that to make a really decent feedback amplifier, you have to maintain a high loop gain over the entire audio range that you need to get the good performance. And that could be a pretty wide window. That is 20 hertz to 20 kilohertz. And suppose you need 40 dB of feedback over that entire range in order to keep the speaker damping factor high over the same range, in order to keep the distortion reduction high over the same range. In other words, your specifications may involve a minimum value of loop gain that you need at some low frequency. So say this might be 20 hertz, and you have a specification of a minimum of 40 dB of feedback at 20 hertz. But you also have to extend that all the way up to 20 kilohertz to get the benefits. So let me shift the scale on this diagram and say this is now 20 kilohertz. I have to maintain 40 dB of feedback up to 20 kilohertz to get all the benefits of feedback up to that frequency. Okay. Now I have this gives me a window of frequency in order for the loop gain to go away. It's going to go to 0 ultimately. But if I put a single pole starting at 20 kilohertz and I have to throw away 40 dB of feedback, which is a factor of 100, then the crossover frequency on a single slope is going to be 100 times 20 kilohertz or 2 megahertz. Now, I can't permit that because I'm not going to be able to control the parasitic capacitances all the way up to 2 megahertz. So, a window is now defined. The bottom of the window is 20 kilohertz, and I have to keep 40 dB up to that frequency, but I now have to impose another side. I have to impose a maximum frequency at which I can allow crossover to occur in order to keep control of and not have the parasitics take over from my design, where the parasitics will something I can't do anything about. So that defines a window. Call it this frequency here. In the case of switching power supplies, this upper limit to the window is half of the switching frequency. You have to cross over loop gain below Fs over 2 to avoid a special kind of instability resulting from the fact that the switching frequency is in there all the time. And if you have a loop gain bigger than 1 at the switching frequency, of course it's going to drive itself directly into oscillation. Anyway, back to the audio amplifier, or whatever the application is, the design actually imposes a window, a certain frequency range over which you have to get rid of all the loop gain. And if you do it with a single pole, you don't make it. You don't fit in the window. So you try 2 poles. And if you put a second pole in, you also have to put a 0 in, because you have to prevent the phase angle from getting to 180 before crossover. And if you didn't put the 0 there, you're already at 180 before you get to crossover, and you have no phase margin. So you have to put a 0 in. And suppose you still don't make the window. Then you have to go to 3 poles and 2 zeros. Now you make the window. But this is a conditionally stable system, because having gone around 3 poles, you're now more than 180 degree phase lag, while the gain is still bigger than 1. And the zeros are put there in order to make the phase come back below 180 as you go through crossover, which is what makes that loop come back around and avoid the -1 point. So it's stable, but it's conditionally stable, and therefore subject to all those hazards that I talked about. Now the important part of all this is, first, the recognition that you may be in this situation. The second thing is, what's the best thing to do about it? And I suggest the best thing to do about it is not to try to design the conditionally stable system because of all those hazards. I suggest instead the better approach is find some other way to widen the window. Because you have other things that you can do to meet the specifications. That is, the easiest thing to do is to lower the requirement for how much loop gain you need at this frequency. If it's a matter of distortion reduction necessary to meet the specifications, then a better way to approach it is to make the output stage more linear. So you don't need as much feedback to get the same answer. And the same thing is true with other requirements as well. There are other ways in which you can reduce the stringency of the requirement, so effectively you can widen the window. And that's a better way to go around the solution than simply try to design the conditionally stable amplifier. Now, that's a qualitative statement, and it's a matter of opinion. But the most important thing is to understand what it is you're working with. Then you make the decisions to do with how you're going to deal with it. Okay, that really is all I'm going to say about conditionally stable systems.